Hello, in this video we will be going through the different steps of processing PSL calibrations. So the basic idea here is that the voltage measured by the scattering detector on the SP2 gives a signal that is proportional to the scattering cross-section of the particles that it is measuring. So what we do is we use particles of a known shape, size and refractive index, and from those variables we know what the scattering cross-section is, and so we can then use that to calibrate the detector. So what we do is we use PSL spheres, which they come in various different sizes, and we know that they're spherical and we know what their refractive index is. And the basic idea here is that you will nebulize your PSLs, you'll put them through a diffusion dryer to remove any water that is remaining on the particles. You'll then put them through a DMA just to remove background particles and then put them into the SP2. Okay, so I've loaded up IGOR here. I've already processed my SP2B files using the LabVIEW code. And so what I'm going to do is load in the SP2 toolkit. Click compile, go to this SP2 toolkit, click yes. And now I'm on load single file here, and I'm going to load in our SP2, our XLS files from the calibration, which is in this folder. I'm just going to check my notes to work out which one. So I've got it highlighted already. So I know X001 is 200 nanometer PSLs. So I need to load in file number 1. And we click filter, and then now the button we click is this one, this pure scatter, because we know it's the vast majority are purely scattering particles. We're interested in the scattering signals that they are giving. So we click that, and this gives us lots of histograms of different signals. I'll maximize it so you can see a bit better. So these top two, you've got the histogram of the full width half maximum of the Gaussian fits to the PSL signals, and you've also got a histogram of the notch position, which is a slightly unusual shape for some reason. And we don't normally do anything with these. I guess it's just useful for diagnostics to see if there's any changes, and you might want to play about with the different fit parameters at some point. But the ones that we're really interested in are these ones on the bottom plot here, and these are the histograms of the scattering signals. So there's lots of different ones here. I guess so that it shows what they are in the legend. I guess I'll just go through them one by one. So pure scatter peak LEO hist is a histogram of pure scatter peak LEO, which is the signal of the leading edge fits to the scattering signals from the PSLs. So that's a good one, that's important. Then there's pure scatter peak hist. You can't actually see that one because it is actually exactly the same as pure scatter peak unfit hist. So I think pure scatter peak hist is the fit height to the Gaussian fits, the histogram of that. And pure scatter peak unfit hist is a histogram of just the height of the Gaussian signal from the PSLs. So that's just if you didn't do a Gaussian fit, you just looked at the height. But it actually comes out the same. So actually, if we want to look at this pure scatter peak hist, we can hide pure scatter peak unfit hist. And look, and now we can see pure scatter peak hist, which was actually exactly the same. There's also pure scatter peak coin. It's a histogram of that. So that's the signal from coincident particles, but we don't actually care about that at the minute. And then down here, this is a histogram of the signal from the low gain version of pure scatter peak. So that's gone through, it's the same detector, but it's gone through the low gain stage, and what this should be is 10 times less than pure scatter peak. So the reason that you might be interested in that is if you're looking at very large particles, then the high gain pure scatter peak, that would be saturated, so then you would look at the low gain detector. So the reason that we have these histograms is that we want to know what is a representative number that we get in these variables from a 200 nanometer PSL or 300 nanometer PSL. And so we plot these distributions, and what you want to know is essentially what is the center of the distribution. And the quick and easy way of doing that, which you might do in the field maybe, is you take this little box with an arrow on it, you hold down Alt, you hold down left click, and then you drag this to the peak position. And so now what you see is this number in the box is the peak position in terms of x on this plot. So it's currently on pure scatter peak hist, so that's the Gaussian fits to the PSL signals. And what we want to do then, I'm going to come out of this, out of full screen, and we want to make a note of this, of where this peak position is. So we're going to add an annotation box, this text just to say, what flight was it? So this is flight CO32, and this is 200 nanometer PSLs. So CO32, 200 nanometer PSL. And what we're going to do is we're going to take a screenshot of this. So what I've just done is I've pressed Control and A just so you have the whole plot. So you've got the histograms of the notch and the full width half maximum, if you want to have those in your notes, which is occasionally useful. And so what I'm doing here, I've pressed Windows, Shift and S to bring up the screen clipper tool, and I'm dragging a box, and then I'm going to paste it into OneNote. So let me make a new page in OneNote and say CO32 PSLs, and I'm just going to paste that screen clipping there. So now we've got a note saying this is the signal from CO32 200 nanometer PSLs. And you may also be interested in knowing, or what is the signal from the leading edge detector? So again, you just hold Alt and hold left click, and you drag this little box onto the other distribution from the LEO hist. And you see you get a slightly larger signal here in this case. So again, we might just want to say, make a note, LEO. And then I'm just going to take a screenshot of that again. Put that in my notes. So, and that's it essentially. That was a 200 nanometer PSL. I'm going to load up a 300 nanometer, just give you another example. So let's come out of this, let's discard this file, and we'll load the next one. And I'll just check my notes again from CO32, which is a flight number by the way. X002 is 300 nanometer PSLs. So I need to load X002. That's loaded in. Click filter, click the pure scatter button, and I'm just going to expand this now, and we can hide that unfit one. And now again what I'm going to do is just hold Alt, hold left click, drag this onto here, and this is now the peak position, the rough peak position for the 300 nanometer PSLs. So let's make a note of that. C032 300 nanometer PSL. I'll just change the scale so it's pretty reasonable. And I'm going to take a screenshot of that and put that into my notes. And now I'm going to do the leading edge. And you can see that one's larger again. Say LEO on it and take a screenshot of that and put that in your notes again. And you will notice, just fortuitously, that the signal from a 200 nanometer PSL is about 10 times smaller than the signal from a 300 nanometer, which is just an interesting little fact that you get. So, and what I'm going to do actually here, just as an example, I'm going to do the low gain detector as well. So again, dragging this onto this different one. So the low gain detector now is giving this signal. So let's make a note of that if we want to do that. And take a screenshot, why not? So you see here that the peak height from the low gain detector is exactly 10 times less than the peak height from the high gain detector, which is deliberate. It is exactly 10 times. Now I've said a couple of times that using this little pointer and picking out the peak position is the quick way of doing it. And the proper way of doing it really is that you want to fit a Gaussian to these distributions. And so I'm going to give you an example of that now. So we'll just find ourselves in the pure scatter particles folder. And so what I'm going to have to do, because the resolution of these histograms is pretty coarse, I'm going to replot the histogram. So I'm going to go into analysis and histogram. I'm first going to go for pure scatter peak, which is the full fitted Gaussian peak height, and we have to set the number of bins. Now I think for the 300 nanometer PSLs, let's try a bin width of 100, bin centered X values, and I'll click that. Now let's try again. Let's try a bin width of 1000. In fact, to tell you what we'll do is we'll try a bin width of 100 and 1000 bins. There you go. So this now is the same data as we had in the histogram before, but just with much better resolution. And you can see it's not really a brilliant Gaussian peak, this one, unfortunately, which I think tells you that the alignment is not perfect. Oh well. So what I've just done there is I've pressed Ctrl and I to bring up these little pointer boxes, and what we're going to do is we're just going to try fit a Gaussian to this peak to try get a representative number. So I've right clicked, quick fit and Gauss, and you get some numbers out here, and it's not a perfect Gaussian, but this is probably a better way of doing it than just having a very coarse resolution and picking the peak. You could pick the peak on a fine resolution, which is possibly a better way of doing it. It's a bit of an open question about whether doing a fit like this or just picking the peak position is the best, because do you want the mean or the median, for example? And this is the way I do it. I do a fit, because it takes into account the whole distribution and not just the peak position. So now let's make a note of this. This is 300 nanometer PSLs, C032, and yeah, it's obviously a Gaussian fit. So this is what I would do when I'm not in the field, when you're looking at your distributions after the fact, and you don't really care how long it takes. So I just made note of that, and then I'll show you that again for the leading edge detector. So analysis histogram, pure scatter peak LEO this time, and click do it. Oh, this is interesting. Sort of a slightly bimodal distribution, but anyway, we'll ignore that. And we'll fit a Gaussian. And see, on this bit it's much nicer fit. And so we'll now make a note of that is 300 nanometer PSLs LEO. And we'll take a screenshot of that and put that in our notes. So one thing I haven't mentioned, with these Gaussian fits, X0 is the part you're interested in. So in this case it's 42,000, this one it's 38,000. And if we look back at our notes, we'll see that these numbers are fairly similar, 42,000, 38,000. There's not a huge difference between what you get from this rough histogram versus the fine detail and doing a fit, but it's the proper way of doing it. It's doing a Gaussian fit. So now that we've got these numbers from our 200 and 300 nanometer PSLs, you should do Gaussian fits to the 200 nanometer PSLs as well. What do we do with them? And we go back to the toolkit here. Where is it? And it's in this panel, this calibration HK correction at the top. And this is the part where you apply the calibration. So this one here is the incandescent calibration. We're going to leave that for now. And this part here is the PSL calibration bit. And so what you can do, you can choose if you want to give it either the signal for a 200 nanometer PSL or for a 300 nanometer PSL. I think in this case we'll do 300. And let's look at our notes. And what I'm going to do is I'm going to choose the fitted peak position in this Gaussian fit for the leading edge detector, because we are normally using the scattering calibration to calibrate our leading edge fits to incandescent particles. We don't normally look at just the pure scattering. So why are these two different? Why are we getting a slightly larger signal from the leading edge fits, 41,833, versus the full Gaussian fit, 38,025, for the exact same particles? Well, it's probably that the alignment isn't perfect, but generally I wouldn't worry about it too much. The only thing I will say is that if you're going to be using these calibrations for looking at incandescent particles where all you have is the leading edge fit, then you should be using leading edge calibration. Having said all that, the difference between these two numbers in terms of diameter is tiny, so actually it doesn't really matter. So what we're going to do is we're going to take this number from the PSL fits, 41833. We're going to go into the toolkit. We've chosen that the PSL cal size here is for 300 nanometer particles, and then we're going to just put that number into this PSL 300 nanometer signal box. What was it? 41833. 41833. Boom. And that's it. You have now applied your PSL calibration. If you wanted to use the signal from a 200 nanometer PSL, you would just have to put that signal in there. So, for example, our signal from the 200 nanometer PSL LEO 4226.98. What we would do is we would put that in this box, 4226.98. Select this PSL cal size as 200 nanometer PSLs, and there you go. That's then the 200 nanometer calibration is applied. And when you click the Generate Single Particle Size button, it will use these calibration values to convert the voltage raw signals into calibrated particle sizes. And that's it. If you take good notes when you do your experiment, then it's relatively simple to get through this quite quickly. Thanks for watching.